Okay, so let's get started with this particular session. So we are into week 12 of Fundamentals of Nano and Quantum Photonics course, and this being offered on NPTEL, and the course instructor is Professor Naresh K. Imani. I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and TU Berlin. And I guess this is the final session of this particular season of the autumn session. So this will be the final week of this course. And what I could see is that there's a little bit deviation from what was earlier depicted in the syllabus. So week 12, instead of covering these time-dependent Schrodinger equations, strong coupling regimes, so what has been covered is something different, maybe something related to the photon number states, and again, a little bit about the field quadratures. So basically, it's all about the going from a classical harmonic oscillator to, uh, I should say, the quantum harmonic oscillator, and all of the notations, all of the operators you get from while going from classical to quantum, that has been basically covered in this particular session. Now, what other things are covered? Maybe applications of quantum, I should say, quantum communications, and maybe quantum key distributions. That has been basically covered in this particular final week. So the content is almost related to week 10 and week 11. So this is all just the extension of that content in order to understand more about the raising operator, the lowering operator, the number state, the number operator, the number states, and the photon number. So all of those things have been discussed in detail, and also about the field quadratures x1 and x2, what we have been discussing from a couple of weeks now, from past few weeks. So now what we are going to do is today again, as this is the final session, and I believe the questions asked are pretty straightforward directly from the lecture itself, and uh, uh, all of the mathematical derivations that has been done by the professor in the class. So I'll briefly try to maybe take 1 hour or 1.5 hour to explain the concepts, and it will be followed by solving the questions. And wherever it's required, I will be explaining it wherever some new things need to be introduced, or maybe some new information may be given. Then that is what I will be basically trying to uh, provide you guys. So, so this is the final session, and I hope I guess I joined this session at around some 10-15 minutes late, as I'm in a different time zone right now. So it's very early in the morning here, so you guys can understand. And let's talk briefly about photon number states. So earlier we talked about, if you know, we talked about something like a quantum harmonic oscillator. If you just quantize the quantum harmonic oscillator, this is the half of kx square, which is the potential energy of the harmonic oscillator. And you can write it as half of m omega square x square, where this m omega square is basically k. So in terms of the simple harmonic oscillator, it is the spring constant. It's the spring constant, or that factor, but it's the stiffness of the spring. But in terms of the, if you write it for the photon, then the mass doesn't exist. Then it has a different meaning altogether. Okay. So I am speaking in a lower voice so that one reason is because my, I should say, throat is not working properly, and I don't want to disturb the other people around here which are staying in the apartment because it's too early in the morning here. So I hope you guys can just raise the volume on your machines. Okay. So this is the parabola is basically the potential profile, potential curve profile, and we are going to say, let's say this is energy, this is x. Then when you go from classical to quantum harmonic oscillator, you say that the energy is discretized, and that is discretized in terms of this particular thing, where you can write it as a dagger a plus 1 by 2, where this n is basically something called as number operator. And I talked about this number operator in the previous assignment problem sections also. I said that if this number operator operates on any of the photon states, this is like photon state. It's a quantum state. Obviously, we're talking about few photons. So if this number operator operates on the particular state, it's going to give you a number and it's going to give you the sum state. So this is the eigenvalue and this is the eigenvector. So this is the scenario. So this number operator, it's now acting like an operator. So this is a dagger a. So this is a number operator now. Okay, so this is the number operator a dagger a, and it is going to give you some number, which is basically a photon number in a state, in a state. Let's say, for example, if you know about this, you know that when you discretize it, you get an E0, E1, E2. It should not be like this. E2, E3, so on and so forth. And important thing about a harmonic oscillator, oscillator. Important thing is this harmonic term is that this spacing is equal. It's equally spaced, and the spacing is h bar omega by 2. Because if this is E0, this is E1, this is E2, this is E3. So E0 is h bar omega by 2. This is maybe 3h bar omega by 2. So this what will be spacing? 3h bar omega by 2 minus h bar omega by 2. You get h bar omega. So pardon me. So this spacing is h bar omega. But it is same everywhere. So I'm talking about this spacing between the two energy levels in a harmonic oscillator. So as you go from one energy level to another energy level, there is a energy difference of h bar omega. Okay, so now what? This equal spacing is important because if you go on studying these oscillator problems, and most of the time the oscillator in a realistic scenario is something called as an harmonic oscillator. And if you have an harmonic oscillator, then in that case, this spacing will not, when you solve the problem for the enharmonic oscillator, this spacing is not going to be same. It's going to be different. Just like if you remember what happens in a quantum well, I'm just trying to relate, trying to make an analogy, I should say, with the electrons' energy states. Okay, if you remember about a quantum well, a 2D well, where the electron is confined in one of the dimensions, you remember, let's say this is one material, this is another layer, let's say this is another layer, it's a perfect rectangular potential well. So let's say this is a conduction band of material 1, this is conduction band of material 2, similarly this is conduction band of material 1, and you can draw the valence band accordingly. Let's not draw it like this. So this is valence band of material 1, valence band of 2, valence band of 1. So now what? You know that when you solve the Schrodinger equation, you get the energy levels as as n equals to 1, then you get it n equals to 2, n equals to 3, n equals to 4. You see what is happening as we are going towards the higher and higher energy levels? The spacing is increasing. Okay, so this is the fact I wanted to make you understand. And why this is increasing, you need to go back to the solution of it and how we basically do the maths of it. Similarly goes for the, let's say, the energy states of the holes. And in a similar fashion, if you have, let's say, something called as high electron mobility transistor. I'm just giving you an example. If you have a, let's say, aluminum gallium nitride and a gallium nitride interface, you have the interface something like this, where this is aluminum gallium nitride. The band gap of aluminum gallium nitride is around 4 electron volts. For the gallium nitride, the band gap is around 3.4 electron volts. And when you just combine these two, I think this is a slight exaggeration. I think I've not drawn it to the scale, pardon me. I've not drawn it to the scale, but this is how the interface looks like. So this is the interface. And when you just combine it, what happens is that there are certain surface states present in the aluminum gallium nitride, and these are like donor states. They donate the electrons. The electrons go down the hill and they come down here at this particular place. And this particular place becomes something called as two-dimensional electron gas. And if you zoom it, it is something like this. It's like a triangular well. So you zoom it, it is like a triangular well. It's a triangular potential well. And when you solve the Schrodinger equation for it, you get the energy level something like n equals to 1, n equals to 2, 3, 4, 5, 6, and so on and so forth. So you know what's happening. So this is n1, n2, n3, so on and so forth. So in this particular case, what happens is that the energy spacing becomes closer and closer as you go on to the higher energy levels, which is opposite to that of this case, to that of the quantum well. Similarly, if you talk about in terms of an harmonic oscillator, let's say you talk about what is an harmonic oscillator. Earlier, this particular term, which is potential energy term, you consider it to be a simple maybe half of kx square term. Now you are going to consider some higher order terms. Let's say x cubed term, x to the power 4 term, so on and so forth. So the potential profile will become enharmonic. And where is it important? It is surely important in understanding phonons because they are also bosons. And the way you treat photons is the similar way you treat the phonons as well, because these are both bosons. They're chargeless particles. They're chargeless quasi-particles. And in that case, you need to consider the enharmonic oscillator. It's very often used to understand the phonon-phonon interaction, something called as phonon-phonon interaction. In that case, this is the exact scenario. Your potential energy profile is no longer going to be a simple parabolic. It's going to have these higher order terms. That's what I basically wanted to make you understand. And uh, this is additional to what maybe you might have studied in this course. So in realistic scenario, all of those higher order terms play a significant role. Even experimentally, you get, because of enharmonic interactions, you get decay, you get loss in the signal, and so on and so forth. So there are multiple effects basically present. And now what we are going to see is, I should say, what happens if we just give me a moment. So if we talk about now the photon number states, just like I talked about what is a photon number state, It's basically the if you have a photon, if you have a number operator, you operate it on a number state. It gives you a photon numbers and a number state and an eigenstate. Just like that. Just like if you have a Hamiltonian operator operated on a wave function, it gives you the energy and the wave function. So this is the eigenvalue and this is the eigenvector. And remember this eigenvalue is actually it is some number. Okay. Whenever you talk about energy, you have certain number, some number. Similarly, this is some number, which is basically here the photon number. Okay. That is why you see that the analogy has been drawn. If you have an equation like this, you can draw an analogy that it's something like En psi n, and you have something like H psi n equals to En psi n, where this energy is basically this particular quantity. Okay, and this is the number operator we are talking about. So I talked about this number operator in the previous sessions itself. Now, what does this number operator do? Let's say you have a state 0 initially. What does the state 0 mean in terms of, let's say you have a quantum harmonic oscillator? We're talking about quantum harmonic oscillator. So let's say you have equal energy spacing. The spacing is h bar omega. This is E0, E1, E2. And then we are talking about state 0, which is this. Let's say this is state 0, this is 1, this is 2, so on and so forth. And in state 0, there is no photon present. Why? Because that's how you get the vacuum state. So this is the vacuum state. And only something called as quantum fluctuations are present there. And how do you get a vacuum state? You have En is h bar omega n plus 1 by 2. When you put n equals to 0, you get E0 as h bar omega by 2. So n is 0. What does n represent? The photon number. If the photon number is 0, but still something is fluctuating there, which is random, which is continuously fluctuating. Just like I told you, whenever you think that, let's say we are talking about state 0, that its wave function will be psi 0 and its energy will be 1/2 of h bar omega. What is this wave function? What does this wave function represent? If there is nothing, then what does this wave function represent? And the main question, which is the important question, is does photon have a wave function? So that is also an important question, and it is a very, I should say, theoretically as well as philosophically, this question has been asked and researched a lot. What does it mean if a photon has a wave function? When we talk of an electron's wave function, let's say we talk of psi of x only for now, ignoring the time dependent part. In the time it will evolve, but for a wave function which is a space in a space, something spreaded. Let's say when you talk about a quantum well, when you talk of a wave function, let's say in n equals to 1 state, remember that for electron n equals to 0 doesn't exist. Otherwise, the solutions will blow up. Remember why? Because the energy E of n for the electrons here is n square h bar square divided by 2ma square, where a is this dimension. And if you put n equals to 0, it will be E equals to 0. There is no energy state. And there's nothing. That's why we start from n equals to 1 in case of the electrons in a quantum level. So if we talk about n equals to 1, we draw the wave function. Let's say if this is a finite potential well, then the wave function looks something like this. This is psi of x. And if you square the wave function, you get a probability distribution. So that basically looks something like this. Okay. This is the tunneling part, leaking part. But what does this represent basically? So this is X dimension. It basically represents there is some spread in the space. There is some probability distribution of finding the electron in this particular spatial region, distribution in the space. But the maximum probability obviously is you can find it at the center. But obviously, because if there is a probability, that means the electron is going here, electron is going here, back and forth. But on an average, when you just compute the probability, it's going to be at the center. That's what the wave function and wave function square is telling you. But what about a photon in a cavity, let's say? If you have a single photon in a cavity, a single photon, it's going back and forth in a cavity, does it have the similar essence of defining, let's say, a wave function in X? Does it have any meaning to represent a wave function in X? Let's say a photon in a state 0 has a wave function maybe represented like this. What does this represent? Does it represent a spatial spread of photon? So the answer is here actually if you remember what we solve for, we don't solve for psi, we basically solve for the electric field. You remember everything we solve for fields, not for the wave functions, right? Even if you solve the Schrodinger equation for the photons, you have to solve it for the electric field, not for the wave function. The wave function is just to represent here. So in an essence, it is basically the field's distribution in space. Obviously, and time is there because in time it will evolve. It will be a time evolution thing in time. Similarly, like if you just bring in the time part here in the finite quantum well problem, then over the time, what's going to basically happen? This is if this was electron's wave function earlier. If you want to know what is psi of x comma t, then there is some finite probability electron will leak. Okay, and once it leaks, with time you're going to see wave function like this, and it'll just it'll just decay and maybe leak out of the bell. That is what happens with your I should say memory systems. In a memory system, when you talk about semiconductor memory, I'm just trying to give you guys flavor because the final session I'm more going to talk about I'm going to talk about more about the application part. So when you talk about semiconducting memory, what causes the loss of data with time? It's basically leaking of the electrons wave function. Because in semiconductor memory there is some kind of a barrier and then there is something where electrons get stored. So these are like oxide barriers or some kind of different materials, let's say. And let's say let's say this is a material with very high band gap. This is another material with very high band gap. So what you do is that you play with these barriers in order to inject the electrons into this region. Okay, and once the electron goes into this region, it stays there. It no longer goes out because it's like now a infinite potential well. It's actually a finite potential well, so that's basically the problem. But how do you inject it? You give some voltages, maybe 20 volt, 10 volt, whatever the voltage level is used to tunnel the electrons. So electrons get tunneled from here From the obviously you have to bring in the electrons, which is basically memory, which is basically a writing operation. That means you are writing some data onto your maybe flash memory, a semiconductor memory, or a solid state drive. Okay, you give some voltage. Now you have when you have to read it, you have to bring this electron back so that the current can flow, and that current value is going to determine what your data was. Okay, whether it was a 1, whether it will be 0, because everything it is represented in terms of ones and zeros. So what current level, what voltage level is going to represent what value of your data. That's how basically data is stored. I'm just trying to give you a flavor of it. But what happens is basically when you just store these electrons inside these kind of a structure, so there are many electrons. There's not a single electron, there's a distribution of the electrons present, obviously. Let's say the electrons, many electrons are present. Obviously they'll be in different states. What happens occasionally and with time, if you compute the tunneling probability, there is a finite, because electron is like a wave function here, it has a finite probability that will tunnel with time. Okay, and after a lot of maybe time, if you don't refresh the memory, if you don't plug it back and so that it can refresh the same number of electrons, maybe let's say if there are 100 electrons here, if 10 electrons leaked out, it's not going to cause a problem to your memory. You can still be able to, I should say, retain your original data. But what if 30 electrons leaked out? If 30 electrons leaked out, you are left with only 70 electrons. And when you would try to read the data, during reading, these electrons have to intentionally tunnel back in order to make the current flow. You have to read it. So when it happens, you're going to only have 70 electrons. That means less electrons. That means less current. And that means your data won't be correctly interpreted because all of these are current and voltage values. Okay? Why? Because I is approximately n q mu times electric field. So if n reduces, current is going to reduce. N is the number of electrons. So that is the important factor, that this time dependent evolution of the electron's wave function, what it causes. Just the basic example I'm talking about. Otherwise, the time dependent thing is a lot of involved thing. So it has a lot of dynamics going inside. So that is what I was talking about. So here, when we talk about for the photon, it is basically the evolution of the field of the electron with respect in space and time. So it's a spatial electric field, and time-dependent electric field is also the oscillating part. So that is what I wanted to generalize. Now that is what the wave function is basically here representing. If you talk about this wave function, it's basically the field's distribution inside whatever you're talking about. That's why whenever you draw for n equals to 1, if you draw wave function like this, for n equals to 2, you draw something like this, something like this. These are basically the field distributions, electric field distributions of the photon. And it's not the probability of finding the photons. It is just like the probability of finding the electrons. It's the field distribution. Okay, and just give me a moment. I don't know what's heating up. Sorry for the interruption. Just give me a moment. I'll be back in a minute. I guess I don't know, my laptop is heating. I don't know why my laptop is heating up. What? Hmm. Okay, so let's try to. What is this timer? Oh, there's a timer on Google Meet now. It's going to end in 28 minutes. Oh, that's not good. So it only allows for 1 hour session. Oh God, I need to inform it to the team. But why my laptop is taking so much of memory? What's happening? Is it this? Okay, so we'll see. So what we are talking about now, if we have a state 0, then your wave function is going to be 0 or psi 0 and energy is going to be this. Similarly, if you have state 1, psi 1, which is the field distribution again I'm talking about, and this is 3 by 2 h bar omega. Similarly, if you go on to nth state, you have the wave function of photon, the distribution as psi of n, field distribution, and the energy is going to be n plus half of h bar omega. So now there are certain things about if you talk about number state, this is a number operator operating on a number state. It's going to give you photon number and the number state. So it's the eigenfunction of the Hamiltonian. Obviously, it gives the number of photons and it's orthonormal. What does this orthonormal mean? That means if you take the product of these, I should say, number states, what is it going to give you? Just give me a moment. That means if you take the inner product, it's going to give you a Dirac delta function. That means for that this Dirac delta function is going to be 1 for n equals to n dash, and it's going to be 0 for n not equivalent to n dash. That means inner product with itself is going to give you 1. That is orthonormal. Okay, so it's orthogonal and it's normalized. So these are two different things, ortho and normal. Okay, and if n is not equivalent to 1, then it's going to be 0. That's what basically the Dirac delta function represents. It's almost like this. So at n equals to n dash, it's going to be 1. Otherwise, for all other values, it's going to be 0. This is something called as inner product. For those of you who know about quantum mechanics, they know about inner product. There's also something called as outer product, which is basically something like this. This represents a different thing. This is used in something called as density matrix. Also is equivalent to some kind of a outer product between the two states. And now what? Now the thing is that I don't want to just go through this again because the professor has talked about it. If you just do some maths, you're going to get that the annihilation operator acting on a number state is going to give you a square root of the number state and n minus 1. So you're going to go down by one state. So if you If you have, let's say, psi 1, you have psi 0, you apply the annihilation operator here, you're going to get one state down. Similarly, if you have, I'm just worried about the timing. Why is showing the timing? Because I cannot see it here. And if you just do it for the creation operator, then you're going to get square root of n plus 1, and you're going to get above 1 energy level. Similarly, you can just what you can do is that they're basically showing that you can create any general state and you can build it up from the vacuum state itself. So if you want starting from the vacuum state, you go up, you apply the creation operator, you are going to get any of the general states. In fact, what we are going to even show you is that the coherent state can be constructed from a number state. Remember the coherent state, it's a minimum uncertainty state. And you remember the coherent state, you draw the field quadratures x2, x1, something like this, where this delta x2, this is delta x1, this is the phasor alpha, which is square root of n, and delta x1, delta x2 is basically 1 by 4, and this is 1 by 2 each, so this is the minimum uncertainty state. Because delta x1, delta x2 can be greater or equivalent to 1 by 4, so at least minimum it can be 1 by 4. So it's the minimum uncertainty state. Now you can just go on operating with the creation operator, and you're going to get this state, the general state. This is almost like a factorial in this representation. This is a dagger operating 4 times on a vacuum state. It's going to give you 1 over 4 square root of 4 factorial. So you can write it as 4 into 3 into 2 into 1, and you can just go on building up the any general states. So now there are certain, I should say, properties of the photon number states, and these are just mathematical properties of this quantum states, and you can just find it on any quantum mechanics book. Maybe you can just go to, I should say, I don't think Mark Fox discussed about it. There's a book called as from the LNSP, who is a Nobel Prize winner on I should say photonics, on this photon states. Uh, he won the Nobel Prize for single photon sources and the experiments on entanglement and other things, proving the Bell's inequality, and that is also almost related to that's how basically they proved the Bell's inequality using the single photon sources. So that's why these are important things. So these are some of the properties that you should keep in mind, and you can derive each of these properties using the some mathematical identities and just going through it. And we're not going to discuss it obviously because Professor has done a great job in discussing these things. So it doesn't make sense to again go back to these concepts. Now what we are going to see, I'm just worried about timings. We are left with 19 minutes. Maybe after 19 minutes, I'm going to relog in into the meeting and then again record it. So that means it's going to overview, so it almost allows only 1 hour. Okay, so we have the first question here, that Hamiltonian in terms of the raising and the lowering operator. It can be written as the Hamiltonian. Okay, so when you talk about h psi n, you write it in terms of n plus 1 by 2 h bar omega psi of n psi of n. So it's almost like an operator acting on a wave function, and it's giving you some eigenvalues of the and some eigenvector, where this En is basically the eigenvalue and is equivalent to this particular thing. And if you have to write it in terms of the lowering and raising operator, then it's going to be in terms of, you can write it in, this n can be written as a dagger a. If you do some manipulation, you can write it in terms of a dagger also, but you will have to, you have get a negative sign here. Otherwise, you'll have the positive sign in case of this is n. So a dagger a is basically the number operator, not this one. Okay, so this is almost like a conjugate. Why? Because if you have a conjugate of conjugate, it's almost like a, it gives you back the previous operator. Similarly, so the answer to this question is a dagger a plus 1 by 2, and this is number operator. Okay, so what else? The number operator is defined as, and that's why he has asked the second question as number operator, which is basically a dagger a. Okay, and this is the number operator, not the a dagger. This is not the number operator. Okay, and now what you can do, yeah, again, the question number 3 is asking, in a vacuum field, there are how many number of photons but dash fluctuations. Just like I talked about that, if you consider the quantum harmonic oscillator, which is almost like, this is half of kx square, which is basically half of m omega square x square in terms of the classical harmonic oscillator, simple harmonic oscillator problem. But this is the energy, this is the x. When you go to the quantum harmonic oscillator, you have the discretized energy levels, just like I talked about in the previous slides, and the spacing is h bar omega. This is h bar omega. And if you have, this is E0, this is E1, E2, E3, so on and so forth, then you're going to get, using the solution of the quantum harmonic oscillator, where the solutions are the legendary polynomial functions, and they look something like this. Okay, so now this is the vacuum field. This is the vacuum energy level, not the field. This is the energy, but you can obviously find the electric field, vacuum field, and that is inversely proportional to the square root of volume. Remember that equation where you equated half of h bar omega vacuum energy to the energy of the epsilon naught v e vacuum squared. So you equate these, this is field. Okay, you equate the both of these energies, and what you're going to get is, I should say, uh, the vacuum field fluctuations, amplitude of that vacuum field. So now the question is saying that in the vacuum field there are dash photons. So you remember E0 you got by putting n equals to 0. That means there are no photons. So that means there are 0 photons, but the fluctuations are finite because the field fluctuation amplitude is this. So you get, let's say 2, 1, 2, 2, 2 h bar omega divided by epsilon naught v square root e vacuum. So this is the vacuum field amplitude, and this is finite, provided you have, if your volume goes to infinity, your E vacuum goes to 0. But obviously you don't have a infinite volume system. Oh, well, what does it mean, if the volume goes to infinity? When we talk about the universe that is infinite volume system, that means your vacuum fluctuation is almost negligible and at a huge level. So that's why these vacuum fluctuations tend to be greater if your volume tends to 0, means if your volume is very small, then your field fluctuations are going to be huge. Okay, so the answer is basically that E vacuum is finite because V is finite for actual real systems. V is finite, which is the volume. So every system is going to have a some realistic volume. It can be no order of nanometers, maybe few nanometers, but it is finite. That's why the vacuum fluctuations are going to be finite. It can be huge, but it is finite. So the answer is 0 and finite. And given below is a schematic illustration of two quantum harmonic oscillators with their corresponding eigenstates. And okay, so this is quantum harmonic oscillator 1, this is quantum harmonic oscillator 2. What are we given? We are given basically the, I don't know why this is popping up every time. So we are given the eigenstates of it, and we have to show what will be the outcome if the number operator operates on these states. What if a number operator operated on the size 0 of A? What do we get? So we get some number, which is basically a number of photons, and size 0, and maybe size 0 of A back, which is the eigenvector. So you only get the information about how many number of photons are present in the state. So you only get that information. Oh, the call is going to end on all of the devices in 12 minutes. So I don't know what to do. Let's I'll end it after 8 minutes, then we can rejoin the call if the Google allowed us to do. So now if you just operate on the side 1A, if you operate the number operator, it's going to tell you the number of photons, and the number of photons is shown in orange circles, which is 3 here. Fine. So you're going to get 3. Okay. And now you are going to operate the number operator on psi 1 of B, and here you have 1, 2, 3, 4, 5, 6, 7. You have 7 photons. Psi 1 of B, you're going to get 7 photons. And I don't know why this 5 is here. Either it is he has given the answer for, if you operate the number operator on psi 2 of B, then you're going to get 5, which is basically the number of photons. Then it would make sense. Otherwise, this is not a correct answer. The answer should be 3 and 7. Because each of the number of photons is basically shown here. So if you operate number operator here, you're going to get 5. This is 2. This is 3. Similarly, this is 3, 5, 7. So that's how it goes. Maybe there is a mistake here. Okay, that's how it works. Now, what will be the outcome if the operator operates on the eigenstate and corresponding energy? Now, if the number operator again operates on a size 0, this is a vacuum state. Vacuum state, I told you, has 0 photons. So the number operator operating on vacuum state is going to give you 0 photons. 0. So number of photons will be 0, but energy for corresponding to E0 is h bar omega by 2. That's, you have En h bar omega n plus 1 by 2. This is it. So you have 0 and you have half of h bar omega. That means it has to be here because at x equals to 0, it's 0. Okay, this is x, this is E, and this is the vacuum state. So you show the vacuum state exactly like this. So let me just follow the same notation. This is the vacuum state. So there is no photon. But when you draw the wave function for a vacuum state, you basically show some kind of field fluctuation because there is field fluctuations are there. So that is what basically the first state wave function or solution is telling you. It's telling you that field distribution, which is fluctuating, but it's like the particles or the photons are popping in and out of existence in vacuum, even in vacuum. So those photons will be having certain field distributions, and that field is basically the E vacuum you compute, given by this equation. Okay, even I talked about if you have a some kind of a metallic if you have a metallic plates, just like a capacitor, but if you have a metallic plates and if you bring them very closer to each other, where the vacuum field becomes huge or appreciable, that means you're going to reduce the volume. You see that there is a force which comes into picture, which is something called as Casimir force. And this is because of the field fluctuations. Okay, because E vacuum field, you can write it in terms of square root of 2. I don't remember the equation. H bar omega epsilon naught V. And if you play with this, you are going to increase this, and you can find the force, the Casimir force from the field as well. Okay, for example, if you consider, let's say, electrons, what will be the force on the electron? By the way, where does that electron come from? It has to be completely vacuum inside. It has to be completely evacuated. It's a vacuum, full vacuum inside. Then only these field fluctuation will come into picture out of nowhere. I don't even know what is the origin of it. What is the origin of quantum fluctuations? Okay, but there will be a force on these plates uh, at certain point because of that vacuum field, and that force is going to be felt by these metallic plates. Okay, and that force is going to play with these let's say the electrons in these metallic plates, and let's say that force is going to be given by some q times the vacuum field, and that will be the force on the electrons in the metallic plate itself because of the vacuum field fluctuations. You remember, because a photon imparts a force. If whenever you have an electron in a field, the force is basically q times E. So I believe we can similarly do such an arrangement here. Okay, and now what we are talking about, fill in the blanks. How much time is left? 5 minutes. This is very frustrating. So, okay, so if you have a creation operator operating on a number state, it's going to give you square root of n plus 1 as the eigen eigen value. Okay, how does it come up? It comes up like this. This is the exact derivation of annihilation. Similarly, it goes for the creation operator. Just go back to the slides, and you get the eigen value. So it increases the photon number by 1. It increases the photon number by 1. So that is what the creation operator does. So this is the exact answer. Now, if you have a field quadratures, you remember this field quadrature we wrote, which was x1 was related to x of t, which is basically position. So it's around, I should say it was related to q of t, which was related to x square root of m, which is position, and this was related to p of t, which is related to momentum by square root of m. Remember? Now you can write the x1 quadrature in terms of the creation and annihilation operator just like this. Similarly, you can write x2 as 1/2 of a minus a dagger. And this is pretty much really important in computing certain field quantities using some sort of a code, because in the code you're not going to write these as equations, you're going to write these as matrix, and there this a is a matrix, a dagger is matrix, a is a matrix, a dagger will be a matrix, and this is a matrix of this sort. A dagger is something like 0 square root of 1 0 0 0 0 square root of 2 0 0 0 square 0 square root of 3, so on and so forth, depends upon the size. And this is basically square root of n plus 1. So now you have to operate it, and you can similarly have a, yeah, you can just take a transpose of transpose conjugate of this. You're going to get the a, and then you need to do the calculations for the field quadratures using 1/2 of a plus a dagger. You need to add one more, you need to add a to it. Similarly, you can subtract a from it, and this is the exact answer you're going to get. This is a plus a dagger. Okay, so for the derivation, I again refer to professor's notes, as I didn't have quite I should say, a lot of time to make these notes for these final sessions, but surely I'll definitely share that if, whenever I get the time. I'll be uploading that in the same drive. So it's showing that the call is going to end in a minute. Just give me a moment so that I can just initiate another call. Oh God, this is frustrating. So we are 57. Okay. I guess I need to first change the time zone. Is it also again? 8:56. Okay. Yes, now the time is correct. Need to reconsider it. Okay, so I'm creating a new meeting link. I think this one has expired, the previous one, so I need to create a new meeting link. I don't know. Okay, so EAF VCPN ZTQ. This goes here. I don't know why that meeting link expired. EAF VCPN ZTQ. This goes off. This goes off. I hope it's recording. Okay, so what I was discussing is, sorry, so the meeting link has changed due to the time restrictions. I don't know why. So the new meeting link is code is EAF VZPN ZTQ. Anyways, this is the final session, so it's getting recorded entirely in this. So now we're talking about what is the fundamental principle behind the quantum key distribution and how does it enhance the security of the cryptographic key exchange compared to the classical methods. The answer is in the quantum entanglement. So QKD, basically quantum key distribution, creates quantum entanglement to create the unbreakable encryption. And I guess I have discussed about this communication between Alice and Bob a lot. That if you have, let's say a source of photons, entangled pair of photons, so that if this source sends one photon to Bob, another photon to Alice, and entangled means that I'll just try to briefly make you understand that if you have, let's say, two photons and these two photons are entangled, that means if now what does this entanglement mean mathematically? That's a different thing. You can write it in terms of just like 0 0 plus 1 1. This is the mathematical representation. How you arrive at it, that's a different story altogether. I'm just trying to give you the flavor. So if you have these two photons that entangled, then if you send two photons this way, if you send one photon the left side on the right foot or right foot on the right side, and if somehow you measure the photon on the left side, and if it comes out to be a horizontally polarized photon, then this will be a vertically polarized photon. That means measuring this photon is automatically going to decide the state of this photon. Okay, so that is as simple as that. That means if you have, let's say, two electrons, and if these two electrons are entangled, what is going to happen if you send this electron right, if you send this electron left, and whenever if you measure this electron and it came out to be upspin, and naturally this electron is going to come out to be a downspin electron. Okay, that means the moment you measure this, you're going to decide the state of this electron. That is the essence of the something called as entanglement. That means these two states are entangled. Measuring this state causes the collapse of the wave function of this state. That is what is meant. So that's why in a single photon entangled pair of photons, if you send one photon to Alice, another photon to Bob, once the Alice measures it, and if she measures that if it's a horizontally polarized photon, the Bob's photon is going to be a vertically polarized photon. Its wave function is going to collapse in on the Bob's photon as well. So the Bob is going to know when Alice has read the photon. So once the Alice reads the photon, reads the information, the Bob is going to know. So that's why if there is like a eavesdropper in between, and if eavesdropper tries to catch this photon, it's going to read the photon. And it's going to collapse the wave function of this photon, as well as the Bob is going to know that somebody has read this photon. Bob's wave function is going to also collapse. I mean, you are going to, because these are entangles, whatever happens with one of the photons uh, is going to be happening with the other photon. Now, there are other paradoxes that came here, that faster than light communication, whether it's possible, how does the information travel faster than light, what is basically happening when you entangle these two photons. That's a different story. That's a philosophical aspect as well as mathematical aspect. Let's not go into that detail. Similarly, let's say if you have single photon streams coming in, then because these are quantum entities, and observing or measuring them is going to collapse the wave function, and you are going to lose the information about that particular state then. That is also a protection against eavesdropping. And that's, I think, I have discussed in week 11 in detail. So that is basically why quantum entanglement is going to be important. And now talking about a coherent state is basically a minimum uncertainty state. That's absolutely correct. That means delta x1, delta x2 is basically 1 over 4. And this is 1 by 2, this is 1 by 2. So this is the minimum uncertainty state. The coherent state is a summation of number states, and the number state themselves are minimum uncertainty state. That's absolutely wrong. A coherent state can be uh, built up from number state, but a number state is not a minimum uncertainty state. That is the exact reason. So the statement one is true, but two is absolutely false because this part is false. Okay, and the widely used RSA encryption scheme, which is used to encrypt, is basically dependent on the factors of the two large prime numbers. Two large prime numbers. So, what is the answer? The encryption uses public keys. That is a product of two large prime numbers, and the time taken to find the factors decreases exponentially with large number of digits. So you have two large prime numbers, and you have to factor them, and how fast you can do is the rate determines how well you can break this RSA encryption scheme. That is what basically protects the banks. That is what protects the data. That's what is basically on the WhatsApp and all other things. But right now, no other computer has the capability to break the factors in a finite duration of time. It's going to take millions of years to break the current encryption, RSA encryption, using the classical computer. But it turns out that if you have a quantum computer, and if you just have 1,000 qubits, then it's going to break this particular RSA encryption scheme. There's something called a Shoes algorithm, and that only works if you have 1,000 error-free qubits, which is right now, I don't know, people are working for it, but once people will be able to find it, then we need to go back and make something called as quantum encryption schemes. Then we need to make it foolproof, so that and we need to completely change the encryption scheme for all our records, banks, and all other things. That's going to be essential, I guess. Okay. And so, okay, the timer has also started on this. So this is it about this particular session. Now, I have not gone a lot into these particular aspects because I guess the professor has discussed about it. I just give you the flavor. And we are technically done with this week 12. And we are almost, I should say, done with the course for now. And there won't be any additional session because I don't think that is required. If you guys have any questions, you can just uh, reach to me over my mail, or you can just talk to the NPTEL people there. Uh, they will give you the information, and that is pretty much about it. So the essential factor is these things you are going to find in a if you want to really understand the quantum aspects, then maybe you can just look at Ellen Espay's book on quantum optics. So this is a particularly a book on quantum optics. If you want to understand quantum mechanics, then you can go to Cloud Cohen Tanoji. I don't know whether spelling is correct, but this is it's like the Quantum Mechanics by Cloud Cohen Tanoji. It's a huge, I guess, two volume book. And for the quantum mechanics, you can go to Griffiths as well. This will give you a flavor of it. If you want to have the understanding of the applied quantum mechanics, then you can basically go to Applied Quantum Mechanics by what was his name? Mm, I'll show you, I guess. Yeah, this one. So, zero. So, this is the book by Anthony Levy. By Levy. By Anthony Levy. So, this is particularly for applied physics as well as engineers. It talks about the maybe fabrication stuff. It talks about quantum dots, single photon sources, and semiconductors as well. What else is there? If you well, obviously there for if you want to understand quantum mechanics, then there are a lot of materials present available online. If you talk about online, then MIT OCW has a three CDs lectures. That is basically quantum physics 1, quantum physics 2, quantum physics 3, and as you go on from 1 to 2 to 3, it's basically going on to an advanced level. But if you just finish those three, I should say, sessions, then it'll be almost like a cakewalk to understand all of the things. Okay, so that's as simple as it. And obviously, then you have their MIT OCW notes. That is just for understanding the quantum because you see the most of the stuff in here is quantum mechanics. But if you are experimentalist, you are obviously going to need it in order to understand, let's say, papers, research papers, journals, and most of the time I have seen that people ignoring the equations whenever they encounter the equations in the research paper, they kind of I should say ignore it and they just scroll it, which I think is not a it is never a good idea to skip the equations because an equation can give you thousand ideas and understanding of the paper. While on the other hand, if you just go on reading the text, you are not going to get much information. But if you just look at the one of the equations, just like you remember, if you know that when we talk about an electron and a positive charge and connected by a spring, remember the Drude Lorentz oscillator model? And this is a classical model, but you remember that electromagnetic wave is treated classically, and these oscillations are also treated like a dipole. And you remember we wrote an equation like something like m d square x over d square plus some maybe gamma times dx by dt plus b dx by plus bx is equivalent to some, let's say, s source term, and this is basically Newton's equation, F equals to ma type of equation, because all these terms are force terms here, and this is basically the source function, and this is almost like an m times acceleration. This should be This is B times V, which is basically a viscous drag type force dissipations. Then there is something like half of kx square type of term should be here, which is basically, but this is energy. You can convert it into force. You can write it in terms of yeah. Let's write it in terms of kx. It's actually kx because it's the force, spring force. F equals to minus kx, Hooke's law. So everything is a force. So you can write k as m omega square x. So okay. So the thing is, now you wrote this equation. Now this equation gives you 1,000 understandings about what's happening to the system. You are having certain acceleration component, you are going to have certain viscous drag, you're going to have certain restoring force, and that is all driven by source function, which is basically a electromagnetic wave. Electromagnetic wave. Okay. Similarly, if you have such a differential equation, you have such a you have these differential equations in all of the areas of the physics. A similar equation, if you want to understand the spin dynamics, let's say a spin dynamics. I'm talking about the electron spin. It can be spin up, spin down, but if you want to understand what's happening it in time, if you place this electron in a magnetic field, then you have an equation called as LLG equation, which is almost like a rate equation where you have the products of, let's say, m cross h, certain factors minus m cross h, and so on and so forth. Plus, there are certain dissipation terms again, plus certain drag terms again, restoring forces, so on and so forth. But the similar equation goes on there. I mean, you just have to look at the equation, you have to solve it in order to understand what's happening to the spin of an electron if you place it in a magnetic field. Instead of just reading the text, memorizing it, if you just understand the equation, just understand what's the source term, you're going to see that you get the solution something like this, like the which basically shows the spin dynamics and what happens to the spin, how does it precess, and all other things if you place it in a magnetic field. That is the essential part of maths, and that's what I always try to, I should say, I always try to make students understand and highlight this fact that why is this particular thing essential. Okay, I believe that is it for now. We are What we are going to do is, now we are almost done with the session. So we lost a couple of minutes in between because of switching to this particular slide. So switching to the particular channel of the Google. So I can see my battery is turned off. So battery is down. So I'm going to turn off my camera, and we're almost done for today's session. So good luck for the examinations. If you have any questions, you can just get in touch with me. Uh, Otherwise, thank you. Bye bye.